Hello class and welcome. So we are still in week 5 and this is a quiz week, and I think in the first class of this week you probably heard the quiz 1 review recording. Hopefully that was helpful in preparing for the quiz. So this class, which is the second class of week 5, I will begin chapter 7 from our textbook, the 6th edition of Sedra and Smith. So this chapter 7 I will cover in this class, and of course these are two recordings, one for the theory and one for the problem. And then I will also take all of next week, which is both classes of next week, week 6, to finish up the chapter. Okay, so that's the plan. So we'll only do part of chapter 7 today. All right, let me expand this to full screen and proceed. So chapter 7, we start looking at integrated circuits and circuit amplifiers. That means the actual chips. So far, most of the analysis we have done are for discrete transistors, and I think by now you know discrete is single separate transistors, whether they are BJTs or FETs, MOSFETs. But so that's the analysis we have done so far. Most of the analysis is still important even as we study ICs, but let me write ICs here so you're not confused. Most of the properties of the transistors are still important, obviously, whether they are discrete or in IC form, but there are some special considerations once you put one of these transistors, or many of them, thousands of these transistors, millions of these transistors, into a chip, into an IC. So that is what is the focus of much of this chapter and many other chapters in the future. Okay. All right. So under chapter 7, we have these 4 topics: IC design philosophy, the basic gain cell, the cascode amplifier, and IC biasing, including a bunch of other topics within 7.4. So today I'll do the first 2, and then we'll do 7.3 in one day next week and 7.4 in the other day next week. These are long topics, lots of problems, so they will take some time. Okay. All right. So let's try and get to 7.1 and 7.2. 7.1 on slide 3 is actually a very short topic. There's not a whole lot. I do advise you to read about this in the textbook. Please read the chapter. In fact, if you want, you should read some other textbooks also that discuss the philosophy between, or the difference between, IC approaches and discrete transistor approaches. If you are interested, they may be helpful. But what I found is there are 6 main items under this topic 7.1 that these are actually, these topics, these notes, this particular slide I got from the 7th edition of our textbook. The 6th edition, it doesn't do a very good job of introducing IC design philosophy, but they've rewritten the chapter, the topics in the 7th edition, so I stole from there. Sometimes I'm going to do that. In fact, for your juniors next year, I think we are switching totally to the 7th edition of the textbook because there's lots of changes. But for you guys, I'm still sticking with the 6th edition because that's what we did last time or last semester in 280. So let's just continue that. Anyway, these 6 topics are or items are, there are differences in how resistors are used in discrete transistor circuits versus IC transistor circuits. So there are differences in how resistors appear, capacitors, power supplies, the magnitude of the power supply, how high should the voltage be, the variety of devices, bipolar technologies, and then CMOS, right? So each of these technologies, each of these items differs or is different between discrete and IC version. So for example, resistors, I think we have already mentioned this maybe, but resistors are difficult in ICs, right? On a little IC to create large value resistances is difficult. With a discrete circuit, you can take a transistor and have all kinds of resistors outside, right? High value, low value, 5% tolerance, 10% tolerance, whatever you like. But with ICs, it is difficult. So that's what this item 1 says. Transistors are used in preference to resistors wherever possible. That means instead of resistors, can we use another transistor? And the answer is yes, because we know transistors can be modeled to behave like resistors, at least in some part of the operating region, right? Not in the active or saturation region, but in some part, the triode part, for example, it's possible to use a transistor to behave as a resistor. So since large and even moderate side resistors have to be avoided, transistors are used. Biasing with constant current sources implemented with transistors operating in the active mode, right? Biasing generally means you need a resistor either in the collector circuit or in the drain circuit, right? So that resistor can be removed if we use constant current sources, and that's what is done in the IC biasing approach. Also, that's what it says. Collector and drain resistors and amplifiers are replaced with constant current sources that have much higher incremental resistance, and thus they provide larger gains. Or biasing with constant current sources implemented with transistors operating in the active mode. So it's also possible to use constant current sources or transistors are in the active mode, that is active or in saturation mode, to kind of mimic a resistor. Okay, so that's that. Next, capacitors. It is impossible to fabricate large value capacitors, small capacitors in the picofarad and fraction of a picofarad range are easy to fabricate, right? So large value capacitors are difficult. So I'm going to put this. But small size capacitors in the picofarad and fraction of a picofarad range are easy to fabricate. So that's why those are preferred. Power supplies. To avoid breaking down the thin oxide layers less than 1 nanometer used in modern 14 nanometer length devices, power supplies are limited to 1 volt or so. That means VDD or VCC is not 15 volts or 10 volts, 12 volts as we see in discrete devices. In ICs, we get down to 1 volts for power supplies. So that's a big difference, right? CMOS technology provides high flexibility with the W and L values of MOS transistors selected to fit a very wide range of design requirements. So you can vary W and L, W by L ratios and get a lot of flexibility with CMOS. With bipolar, BJT circuits can also be combined with CMOS in innovative and exciting ways in what's called BiCMOS technology. So apparently this is also important from ICs. Lastly, currently the vast majority of analog ICs are designed using CMOS. So CMOS technologies has come into analog also. We know that in digital they are very popular for implementing logic circuits, inverters and so on, AND gates, NAND gates. But if you are thinking, oh, BJTs are good for analog, that was true, but apparently CMOS is also doing a lot of, has become quite popular with analog. So based on all this, I can tell you that at NAU, with some of the more senior professors who have been teaching these courses for a long time, much of the focus has shifted to CMOS. BJT, they don't feel it is necessary to treat it too deeply. So we will do a little bit of BJTs here and there, but the focus both for analog and digital will mostly be moving to CMOS. So that's one thing that I'll leave you with. I'm not willing to give up BJTs yet. We'll do a little here and there, particularly amplifiers. They're still very popular. So we'll do a little, but mostly as you do more advanced courses at NAU, you'll find that we are spending more and more time on CMOS, MOSFET, circuits. All right, so that was it for the first topic in section chapter 7. Now we'll move on to the next topic, which is 7.2, and spend the rest of this class on this. And also problems, they're all, in my next recording, they're all on 7.2. There's very little, nothing on 7.1. All right, so 7.2 is the basic gain cell. And it has 1, 2, 3, 4, again subtopics, and we'll go through each one of these in some detail. And then let's see, depending on time, I may do an example or two also in this recording, or do it all the problems in the next one. So the basic gain cell, the idea in discrete transistors, as you very well know from the previous stuff that we have studied on amplifiers, that the gain where you want the highest voltage gain to be achieved, that means V output by V input as high as possible. The most popular or the mostly used gain cells or gain configurations are the CE and the CS configurations, right? CE, common emitter when it's BJTs, and common source when it is MOSFETs. So we already know that these are used for gain. Now we have the other configurations like the common base, the common gate, common collector, common drain, CD. These have other functions, particularly they're mostly unity gain, right? The gain is supposed to be 1. Also, they have they're used for impedance matching. That means when you have a source generating a signal that has a low output impedance, then when you want to connect it to a high gain CE stage, you put a buffer before it, right? You put like a common base. Similarly, on the output, if you want to match the high output resistance of a CE amplifier, if you want to match that to a low input impedance source, not a source, but let's say an output device such as a speaker, right? I've talked about this in the past. Then we use the CE stage. Sorry, not the CE. The CE is the gain stage. We use the CC or emitter follower stage, right? So that was just a revision of how we have studied these various stages. Now, because we have come to ICs, we'll first focus on the basic gain cell, which is again your CE and CS amplifiers, but with slight modifications to make them more suited for IC design, IC application. Okay, so that's why we are studying CE and CS amplifiers, which we have studied a lot already when we did discrete, but now we are studying them again because now we are looking at IC based amplifiers. So gain is still important, right? Gain is the most important function in an analog application. Gain meaning voltage gain, current gain, right? These are the important applications. So that's why we are studying them first. Okay. So let me move on to slide 5, where we look at topic 7.2.1. So again, we are going to study CS and CE amplifiers, but this time with current source loads. So the load is in the collector circuit for a BJT, and it is tapped off the collector circuit in a BJT, and it is tapped off the drain circuit in a FET. So here you have the drain circuit from where you get the output. So the load goes somewhere here. There is of course a resistor here always, right, RD, and here in a BJT circuit, this is a N-type MOSFET and this is an NPN transistor. So here again you are tapping the output here or here, and normally you have a RC, a circuit, a resistor in the collector arm that helps you regulate your output voltage, right? So now you'll notice when we are studying the basic gain cells of IC amplifiers from figure 7.1 that those resistors are gone and we have current sources, right? A constant current source. You know what a constant current source is, I hope by now. Whatever is the loading, whatever is the changes, a constant current source or an ideal constant current source gives you an absolutely steady fixed current value, right? Now we can study current sources later, and they are obviously again created using transistors. So it's kind of, you need one to understand the other. But for now, just believe that we have been able to create these constant current sources I that are shown here. Okay. So the basic gain cells in ICs are similar to the CS and CE amplifiers seen earlier in discrete applications, except that the resistances RD and RC are replaced with constant current sources. These circuits, like these two, are said to be current source loaded, or they are also called active loaded. Okay, so if there is no resistor but you can see a current source, then you call it a current source loaded amplifier or active loaded. Now one last thing is, both the MOSFET and the BJT are operating in the active region here, right? This and this, we're talking about saturation here and active here, not cutoff, not triode, none of those other regions. Saturation and active, but for convenience, even saturation here is just called active. Okay, so I hope there's no confusion by now. Active meaning the linear range where most amplification is expected, right? So that is the basic introduction to your current source load gain cell. Okay, so this is figure 7.1. You can see the schematic. Then you can see the small signal model, right, for the BJT here and for the FET here, right. Now for the BJT, there is always an input resistance that's finite, and that's given by R pi, right. So there is a Vi is a signal source, and then there is R pi, which is the input resistance. Sometimes there is a signal resistance also, or the signal source has a resistance. So ignore all that for now. The blue block is the small signal equivalent, and in the small signal equivalent, what is the value of the current? It's transconductance times this V pi, which is the voltage drop across the R pi. You also have an RO, the output resistance due to the early effect. So the voltage, output voltage, which is here and here, is what is on this parallel branch. Same thing here for the BJT. Here we don't have an R input, it's actually infinity, because the gate, we know, has no current in it ever, the gate circuit. So it's like an open, hence the R input is infinity. Here R input is R pi, right? So this is open. But there is a voltage VGS, which is most likely this voltage. And the current, which is the model that we use, that means the voltage here is converted into a current. That current is the product of transconductance times this voltage, right? In parallel, there is the same RO. So that is the model of the gain cell, the current source loaded gain cell, and the amplifier parameters that we have talked about in the past, Rin, Ro, and A open circuit voltage gain. These are also shown here. They were not in the original drawing, but I brought them in so we can start looking at them right away. So the open circuit voltage gain is a negative, and it's GM-RO. Same thing, open circuit voltage gain is a GM-RO. GM is the transconductance of the device. Here Rn is R pi, Ro is Ro, Ro is Ro. Okay. So that is this slide, and it's time to move on. This was slide 5. Let's move on to slide 6. Okay. So we define something now called intrinsic gain. Is the maximum gain obtainable in a CS or CE amplifier? An IC, I guess I should say that. Okay. In an IC form of the amplifier, we are defining a new symbol A0. Sorry, A output, AO. AO is the maximum gain obtainable in integrated circuit, CS or CE amplifiers. And there is a lot of material on all this. It's a long chapter. Again, I advise you to read the chapter at least once, maybe twice, so that you know every sentence, or you read at least every sentence in the textbook to explain all these concepts. Obviously, I cannot sit here and read every one of those for you myself. We just won't have enough time. but I'm trying to highlight the main important points. So there is a new symbol AO that is defined, and AO is GMRO. So for some reason this was considered important to define and distinguish from a VO, which we have already seen, right? In this case, there's a negative sign for a VO, but the new symbol intrinsic gain, this portion, is without the negative. So it's just defined using these two quantities, GM and RO, but without a negative sign. Also, what you'll notice here is AO in both cases are very process dependent. That means they don't have too much influence from other circuit components, but they depend on mostly on the technology, right? So VA, for example, the early voltage VA is fixed for a BJT technology, and same thing for a MOSFET technology. VT, the threshold voltage, for a BJT is about 25 millivolts, that's fixed. And V over voltage also, while it depends on the gate to source voltage, it also depends on the VT, the other VT, the V small t, right? Actually, I think small t is the threshold. VT for BJT is the capital T is different. But the VT, the small VT, both N and P type, is also a technology dependent constant, right? So, bottom line is the gain, the intrinsic gain, this ratio is generally between 200 volts per volt to 5000 volts per volt for a BJT. For a MOSFET, it is 20 to 40. So see the difference? These numbers are almost 10 to 100 times, right, bigger than these numbers. So the MOSFET gain is much lower, the range is much lower compared to a BJT gain. That's why BJTs still haven't died, right? They can offer quicker gain because of the advantages they have. Certain other advantages are in favor of the MOSFET, but at least as far as the gain goes, you can see the big difference in the intrinsic gain. So these formulas are in the textbook. Please take a look and become familiar. This is VA divided by VOV by 2, and V over drive voltage for MOSFETs. It can also be shown to be this. Now this VA prime is probably something we haven't talked about too much in the past, but here's a definition of VA prime. For MOSFETs, it's given, a lot of problems are given in this form. Length is the process technology length, right? We call it 18 micro product or 24 micro MOSFET, right? Or even 14 nano is what they're coming up with now. That's the latest technology in mass production. So L we know, VA prime is given, and then we can always find VA and then use it in this formula. So this can be written like this, right? The 2 goes up, the VA becomes VA prime into L. And then there is this in the middle. If you are given a lot of this stuff, like the mu n COX value, and if you know ID, so even without a knowledge of the overdrive voltage, you can still find the intrinsic gain. I guess you can either, if you have VOV, great. If not, if you're given ID, also you can find A0, AO. the intrinsic gain. In problems, I just wanted to point out this many times, so right away I'm pointing it out. The L is directly given in micro. So if you see an L given in micro, you don't have to put into 10 to the power minus 6 in the formula. Just use the value directly in this formula and it'll work. Okay, so I caution you about that right up front. All right, so we have problems on this topic, how to use all that we have learned so far just to get a output. So we'll come back and do it later. But let's move on with the theory and look at the next slide, which is slide 8. Effect of the output resistance of the current source load. So we said we are going to put a current source load, and that current source obviously isn't like a magic. It comes with its own issues. And we know that a current source generally is shown in parallel with a resistance, while a voltage source has a series resistance, right? That's the Thevenin model, Norton model. But a current source always has its own output resistance, and that is shown in a model as RO2. RO1 is for this transistor, and here what you see is the current source that we stuck here, right here, is, like I just said, is another transistor. But in this case, it's a PMOS transistor. So a PMOS transistor biased in the saturation region provides the required current I. And with certain tricks and techniques on how to bias this transistor, the PMOS, in the saturation region, you get a very good constant current I. Not variable, but a fixed constant current source I can be made available using a PMOS transistor. So we'll do that in the fourth topic, not 7.2, but 7.4 deals with these kind of issues a little more. So for now, just take it that a PMOS transistor will do the job. When we go to 7.4 next week, we'll spend more time looking at this arrangement, and there's a few other arrangements also to give us this constant current. So we'll talk about those next week. For now, just understand that there is a PMOS transistor, it has its output resistance, and for the final model then, this resistance becomes in parallel with our small signal model. So all you're doing is taking this and sticking it here. The current source of the CS amplifier can be implemented using a PMOS transistor biased in the saturation region to provide the required current I. Now the total voltage, overall voltage VO by VI, in this case VO by VI, is now GM1 of this transistor. We don't care about the GM of this transistor, the transconductance. This is the amplifying transistor, the NPN transistor. Its GM multiplied by RO1 in parallel with RO2, right? This combination. So what happens when you have two resistances? If you didn't have this, this would have been just RO1. But the moment you bring another resistance, assuming it's the same as RO1, then the resulting resistance just becomes half, right? Because there are two parallel paths and the net resistance is half. So the voltage gain drops. So the finite output resistance of the current source load transistor reduces the magnitude of the voltage gain. So this voltage gain severely falls because of this. Okay. So as it is, the MOSFET has low gain. Now the gain is even further reduced. Okay. Here's another current source load. Okay. Here it's more complicated than just this, right? Here, this is the amplifying transistor, the gain cell Q1, which is an N type. Here we have two P types. Did I say P type here or did I say PNP? I hope I said P type on the previous slide also. So we have two P types which create the current source. And that current, and this two combination is called a current mirror. So the current source load of the CS amplifier can be implemented using a current mirror circuit. Now we have seen a current mirror circuit, but we never did much work with it. But it's appearing again. And again, I promise you, when we look at topic 7.4 next week, we'll study current mirrors also. So again, bear with me. We'll do more analysis next week. But for now, just understand that instead of having just one P-type transistor, PMOS, here you can have a combination, a two pair combination that makes for a even better source, an I reference source, than just with one PMOS. So the current source transistor Q2 is the output transistor of a current mirror formed by Q2 and Q3. So you have Q2 and Q3. Q2 is called the output transistor because that's where the output of the whole circuit is coming out of, while this Q3 actually provides the reference current, the I that we are so interested in, to help with biasing this Q1. Okay, so this I, which also flows here actually, and we'll learn more about this current mirror operation next week, but this I reference, which is coming off of the drain of this PMOS, that's what we require from this circuit. And we have this pair of PMOS transistors to give us the current mirror. So this is another way to create the biasing for our current load amplifier, right? The current source loaded amplifier on a integrated circuit, both the MOS version, it can be implemented using the one PMOS device or a paired PMOS devices in a current mirror configuration. Okay, so the input is still on the amplifying transistor, its gate terminal. So you are applying the input Vi to the gate to the common. The common we know is the source terminal, and the output we are getting from the drain of the amplifying transistor Q1. The output is coming drain to ground, and ground is again the source of Q1. Okay, so you can see Vi and Vo. Okay, and of course this I reference is the biasing of this device. So more details on current mirrors later. There's a couple of problems. There's actually a good example in the textbook on page 500, which we'll look at next time. And it's a lot more complicated to understand, right? The current mirror has all these things happening. So the transfer function Vi or Vo to Vi, you have to keep considering these different transistors, particularly Q1 and Q2. So all that is, we are introduced to that in 7.2 and 7.3, but we'll look at it later, and then also next week when I do 7.4 section. Or 7.2, 7.3 are our examples, by the way. All right, So a couple more topics and then we have to close this. Increasing the gain of the basic cell. So the gain, the intrinsic gain, we know is Gm into Rho, and we know the overall voltage gain is also dependent on these output resistances. So we need to raise the total resistance here, right? The more we get this, the higher the gain. Pretty simple. So raise the output resistance of both the amplifying transistor and the load transistor. So the amplifying transistor is here, the load or the current source transistor is here. If we can raise the output resistance of both, that would be wonderful. So how do we raise it? Imagine putting a box, they call it a black box, right? We don't know what's inside, but imagine putting a black box. All it has to do is not mess with the current, keep the current the same, the biasing current, right, the same, but just raise the resistance by a factor of K. K may be 10, 100, whatever, right? So whatever is this resistance, just multiply it by a value K. Can we do that? That would be wonderful, right? Then we can say the gain of this whole circuit has increased. So that is achieved by using what's called a current buffer. The black box passes the current unchanged but raises the resistance level, hence it is a current buffer. CG and CB circuits have a unity current gain and are used as the current buffer. So we have studied common base and common gate circuits. So those circuits are what we'll stick here in the middle. So now you can see this whole amplifier, the basic gain cell, is getting more and more complicated. In ICs, right? It's not just a simple circuit with a drain resistance, a simple FET with a drain resistance. Now we keep adding new and new things, including a couple extra transistors or many more transistors we've already seen. Okay, two important final comments about raising the gain. It is not sufficient to raise the output resistance of the amplifying transistor only. We also need to raise the output resistance of the current source load. Obviously, we can use a current buffer to do this also. Placing a CG or a CB circuit, common gate or common base circuit, on top of the CS or CE amplifying transistor to implement the current buffering action is called cascoding. And that is the topic that we will look at next. Okay? So, sorry. After this, we only have problems. So I will wait to do all these problems in my next recording. And we are almost out of time. So just to summarize quickly, in this session, we were introduced to the idea of the gain cell, which is the CE or CS amplifier, with certain modifications that are important if you're going to use the CE or the CS amplifier for gain purposes in an IC, in an integrated circuit. So if you want to use it, then we have to start messing with current sources, either a single PMOS current source or a current mirror which consists of two. In addition, we need something called a current buffer, which only reason it's there is to increase the resistance so that the overall gain is still not too low and can be used, can be high enough to be used for actual practical applications. So that was a summary. One important thing I wanted to show you, I think you should take a look at the appendix in chapter 7. This is a unique appendix. It is attached to a chapter, not to the end of the textbook. But in chapter 7, in appendix 7.a, there is a lot of comparisons between MOSFET and the BJT. Lots of good notes, good tables like this, technology, device parameters for MOS, for BJTs, everything that we have studied so far, it's all shown here. Then there is a comparison table 7a3 that goes on and on. It revises what is a forward bias junction, reverse bias junction, how does a MOSFET operate, how does a BJT operates, what are the current formulas. All this is there. So I suggest you spend a lot. I may not have too much time to spend on this, but if you're struggling to understand the basic theory and the logic of each of these separately, BJT versus FET technology, but also how they compare to each other, this appendix 7.a is your friend. So go ahead, spend time on that. It'll help you. All right, with that I stop this recording and we'll come back and do problems next.